Welcome to your fourth lesson in Chapter 1. This is the last lesson in Chapter 1, and it covers sections 1.6 and 1.7. Text is 57 through 73. We're going to talk about several different operations that you can perform with functions in these two chapters. And if you'll notice here at the beginning, I have function f and function g. We usually use f and g, and then we may throw in an h every now and then. But if you have two functions and you are adding them, that's the same thing as taking each of the functions and add them up initially, or separately. In other words, take both functions. You can do the same thing with subtraction. You can split that up. Just because of the parentheses there, that doesn't mean you distribute the x. All right, you're taking each of those functions. Here, you're taking the function. It's not just fg times x. You're taking the function f times the function g. And division is the same way. But you need to remember that if you have the function g in the denominator, that function cannot be 0. Now, I will ask you to simplify the following, or perform the following operations on the functions. You need to remember to watch for combining like terms. You may need to distribute different coefficients, and you always follow the order of operations. So make sure that you do that. Okay, let's talk about another type of operation with functions, and that is called the composition of functions. When you have a composition of functions, it actually puts, just like a composition would be putting two pieces together, that's what this does. So it combines these two functions. For example, if I have the function y equals x squared, and then I have the function y equals x to the fifth, if I put this function in this function, I would have the x plus 5 squared. All right? So when you are putting functions in functions, we denote it again with f and g. So, for example, you would evaluate one function first by using another, but the order matters. If you have, we write this, f, and then there's an open circle. That's different than a closed circle, because the closed-in circle would mean multiplication, right? The open circle means composition. This means if you have f composition g, that means that you are putting g into f. And you can also write it this way. That means you're taking function g and you are putting it into function f. Now likewise, you can have g composition f, which means that you are taking f and you are plugging that in, substituting that in for the function in g. So you read this, it's either f of g or f composition g, or g of f or g composition f. All right? So if we pick an example, I'm going to let you write that down. Example 1, if the function f is 3x plus 1 and the function g is 5 minus x squared, if I first want you to find f composition g, that means I'm putting g into f. That means I'm going to take the function g, the 5 minus x squared, and I'm going to plug that in to f where I see x. So I would take that value and plug that in there. So I would have 3 times 5 minus x squared plus the 1. Okay, distribute. I distribute that, and I get 15 minus 3x squared, right, plus 1. I can combine the 15 and the 1 to get 16. That's my answer. 16 minus 3x squared. That would be that composition. Now another thing you might have to do will be to evaluate a composition at a particular value. So I want to evaluate F composition G at 3, for example. There are two ways to do this. If you've already done the F composition G, it's kind of easy, because if you've already done this, then method 1 is just come over here and evaluate it at 3. Plug 3 in there, that's 3 squared, that's 9 times 3, all right? 3, then you're going to have 9 times 3 is 27, 16 minus 27, you get negative 11. Okay? Method 2 states that if you pretend you hadn't done this, and you just are looking at this composition, you're going to evaluate G at 3 and then use that into F. So we're going to evaluate G at 3 first, and then plug that value into F. Here's G, 5 minus x squared. So we need to do 5 minus 3 squared. We're evaluating it at 3. That's 9. 5 minus 9 is negative 4. The function at negative 4, f at negative 4, means I go back to function f and I plug in negative 4. So I have 3 times negative 4 plus 1, and that gives me negative 12 plus 1. Oh, look, it's also negative 11. So, I mean, that's good, right? We did it two ways, we got the same answer. But you can evaluate it either way, but method 1 is easier if you, as I said, if you've already done the composition. Let's look at another example. Example 2 says if the function f is x squared minus 2 and g is the square root of x minus 3, find f composition g. Well, we need to establish some things right away. This radical function has a restricted domain, right? Because we need this value to be positive. So the domain right here, the domain is going to be restricted such that x has to be larger than 3. If I put in a number less than 3, I'm going to get a negative within that radical, and I can't have that. So I need to have this restricted domain. So let's find the composition. The composition of f and g is going to be f at g. So that means I'm going to plug in g, which is the square root of x minus 3. And I'm now going to take that value, f at the square root of x minus 3, would plug it in here. So that's going to be the square root of x minus 3 squared minus 2. Well, the square root of x minus 3 squared is simply x minus 3. Minus 2 is going to give me x minus 5. So the answer is x minus 5, where x is greater than 3. You have to include that extra part of your answer because the domain is restricted for the g function. Okay? Let's talk about inverse functions. So far we've done operations and we've done composition. Now let's talk about inverse of a function. Inverse function has some criteria. So very often I will ask you, I will say, does the following function have an inverse? So if a function has an inverse, there are 3 things that happen. If it has an inverse, the function passes the horizontal line test, meaning you can draw a horizontal line across that function and it only touches once. Okay? Number 2, the x and the y can be interchanged, meaning if I have a t-chart, I can just flip the x and the y, and I can get the new function. I can get the inverse. Also, the inverse is a reflection over the line y equals x. So very often we draw that line and see if the inverse reflects over that line, if that's possible. Then you have a function that has an inverse. So we're going to try an example. This example says state if the function has an inverse. If so, tell me what it is, state it, okay, and figure that out. So the first thing we're going to notice is that this is square root function. So if you remember from your parent functions, you should have an idea what the graph looks like. And let's go ahead and graph this function. If we graph this function, if I plug in 1 right here, 1 minus 1 would give me 0. So I would have the point 1, 0. If I plug in 2 minus 1 is 1 times 2, right? I'm going to be at 2 times 1. That would give me, if I have 2 here, that's 2 minus 1 is 1. 2 times 1 is 2. So I'm at 2, 2. Okay. If I can only take the square root of, let's make that 4, so I need this to be 5. If x is 5, let me write some of these down over here. If x was 1, then I was at 0. If x was 2, I was at 2. If x is at 5, I'm at 4, right? Because 5 minus 1 is 4. Square root of 4 is 2 times 2 is 4. So we have a function that looks like this. Okay, does that pass the horizontal line test? Yes, I can draw any horizontal line there, and it's only going to hit it once. Can the x and the y be interchanged? Well, let's try. These are the x and the y for the given f function, so let's interchange them. I'm going to make all my y's my x's, and my x's become my y's. Let's graph that. 0, 1 would be right here. 2, 2, same point. 4, 5. 2, 3, 4. 2, 3, 4, 5. So I have this. Let's make that a different color so we can see it. Okay, so I have the inverse is pink. Let's talk about the domain and the range. Okay? The domain and the range are also, we've done that in the past with radical functions, and I think this is a good place to stop. We'll do the domain and the range and actually state the inverse when we come back in part 2. All right, I'll see you then.